Hello and welcome to everyone. So today we'll discuss the 49th lecture on the course of financial econometrics. In continuation of the last class, today we'll also discuss about the volatility models. So basically this model is an extension of the previous model which we have discussed into the last class, that is the GARCH. So this model GARCH, which basically stands for generalized autoregressive conditional heteroscedasticity model, was introduced by the Slave in 1986, and it is an extension of the previous model which we have discussed into the last class. It is quite widely used in economics and finance to model the and forecast the time varying volatility of the financial assets. For example, stock returns, exchange rate, commodity prices, etc., etc. So you can recall that in the last class what we have discussed, that arch model of, here we are concisely representing that arch model of order Q, which is HT, that is the variance, omega plus the squared past term of the error terms. So here HT is the conditional variance. At time t, it depends on omega, a constant term more than 0, and the past terms of the squared of the errors up to like q. However, what we have observed in the last class, that there are the certain limitations of these models we have. One of the limitations is that a large number of parameters we have to estimate to fit the model into the particular financial data. However, when we have large number of parameters, then the problem of degree of freedom may emerge. And we know from the principle of parsimonious, the smaller the number of parameters, the better the model is assumed. The second limitation of this arch model was that it cannot capture the leverage effect. What is the leverage effect? Already we have discussed. Let's quickly revisit it, that what the financial data often show the characteristic that the positive change has the different effect on the volatility, and the negative change has the different effect on the volatility. In general terms, what we know, the good news and the bad news both have the different effect on the volatility. It has been observed quite often that the bad news has more intense effect on the volatility, whereas the positive change or the positive news had the smaller change on the smaller effect on the volatility. Second, it has been observed that arch effect is often poorly fit into the data. The fourth, if the limitations we have observed into the arch, that sometimes it is quite difficult to maintain the non-negativity constraint, and sometimes it may violate that particular constant. And if that is violated, that means we are showing that the variance could be negative, which is against the theoretical concept, because volatility cannot be negative. So to overcome certain issues of this arch model, there was the general there is natural extension of this model, what we call a GARCH model, that is generalized autoregressive conditional heteroscedasticity model. One of the simplest form of the GARCH is the GARCH-M, and it has been observed most often the GARCH-M is enough to model a particular financial data. So GARCH-M, when we say, basically it reflects that there is the one arch term and there is the one GARCH term. And following the suggestion that it is better to simultaneously model both the mean and the variance equation. So let us say we have a series. Let's say that is the return of the stock prices represented by RT. It could be modeled, the mean equation could be modeled as mu plus epsilon t. Here epsilon t is the error term, which follows a normal distribution with mean 0. However, the variance is HT. That means we are not assuming variance is constant, rather than we are assuming variance is time varying. And that time varying model of variance, that is how the variance evolve, that can be represented by the variance equation, where we are assuming that variance depends on the omega, a positive constant, and it also depends on the squared path residual, and it also depends on the past value of variance. So this particular term, what we call the arch term, and this is what we call the GARCH term. So this particular equation here shows that the variance of the, or the conditional variance of the error term at time t depends on the one leg of the past squared error terms, and also it depends on the just immediate past value of variance, that is its own, where this alpha, that is captures impact of the past squared residuals, that is the arch term. On the other hand, this beta, it captures the persistence of the past conditional variance. Now higher the value of beta, higher the persistence of the variance. What we mean by the persistence, that let us say if this ht minus 2, that is the variance of the second 2 period back, has impact on the variance of this current period. So that how much it has effect, or in other way we can say how much the variance of the current period depends on its own previous values, that is the persistence of the variance. Now what are the key features of this model we have? So one of the key feature is that this particular model is able to capture the volatility clustering, which is quite often into the financial data. What is volatility clustering? Already we have discussed, so quickly we can say here, the higher volatility in the previous period is followed by the higher volatility into the current period. That means if there is the higher fluctuations in the previous period, that will be followed by into the current period also. If there is the smaller change, a smaller fluctuation in the previous period, the current period will also have a smaller fluctuation. So that's what we mean by the volatility clustering, and that phenomena can be captured through the GARCH model. And the term epsilon t minus 1, that is the past square error term, through that we are able to capture, and also through the past variance volatility or the variance we are able to capture. Second key feature is that it is mean reverting, that is the conditional variance reverse to the long term average. Third, if the value of alpha plus beta is less than 1, then this variance equation is stable. Fourth feature, it is quite simple here in the computation and also in the estimation. Why? Because we have to estimate only 3 parameters, that is omega, alpha and beta. We have seen in the arch model that most of the time we have to have the large number of parameters. However, can we use the OLS to estimate this particular model? No, we cannot use that, because this is not the usual linear model which we have discussed in the previous lectures. This has a different structure, therefore for the estimation we need a different tool, different methodology. So for that we resort to the maximum likelihood estimation. So this is the maximum likelihood function. To estimate the parameters omega, alpha and beta, we maximize this log likelihood function. So given the data, we maximize this log likelihood function to get the value of omega, alpha and beta. Often we use the numerical optimization techniques, for example BFGS, and there are the other techniques we use to estimate this particular model. As we have generalized in the arch, similarly we can also generalize the GARCH model. Here we have discussed GARCH 1.1 that can be generalized to the GARCH PQ, where the P indicates the presence of arch term, Q indicates the presence of GARCH term. So here we can see this, we can formulate a GARCH PQ model, that is arch, there is the P arch term and there is the Q arch term. where we have non-negativity constant, that is beta j, it should be more than or equal to 0, that effect of the past conditional variance. And on the other hand, alpha I plus beta j is less than 1, which basically ensures that the variance equation does not explode and it is a stationary equation. What are the advantages here we have? Simple and easy, it is easy to implement because a very few parameters has to be estimated. Second, it captures the volatility clustering effectively. That is, the large changes will be followed by the large changes, large fluctuation. Smaller fluctuation will be followed by smaller fluctuations, which is quite often has been observed among the financial data, that it is captured effectively, that particular phenomenon. Third, it is very suitable for the short-term volatility forecasting. However, there are the certain drawbacks we have or the limitations we have. That first, it is assuming that asymmetric response, that is to positive and negative shocks. That means if there is the positive change, it will have the same impact as it has a negative change. That means it does not consider the sign of the change, rather than it also considers the volume of the change or the quantity of the change. In the real world, it implies that both bad news and the good news have the similar effect. However, it has been quite often observed that bad news and the good news both have the different effect on the volatility. That means it does not account the leverage effect. Second, this GARCH model may not be captured the long memory in the volatility, that is the higher persistency. Second, as we have the problem in the GARCH model, here also it is sometimes it is difficult to maintain the non-negativity constants. Then, to overcome of these certain issues, there have been many extensions of the GARCH model. Few of them will be discussed in this lecture here. So let us discuss the first extension, that is the GARCH-M model, or what we call it GARCH in mean model. So what is the GARCH in mean model? Basically, we incorporate the variance into the mean equation. So that's what we call the GARCH in mean model. So we bring a conditional variance into the mean equation. This was proposed by Angel, Lilin and Robbins in 1987. Basically, it captures very important phenomena, that what we call the risk return trade-off, by linking it into the mean equation. So let us see what we mean by here. So that mathematical formulation of GARCH in mean model could be that RT is equal to mu plus lambda into FHT plus epsilon T. So this term, which is basically the conditional variance, we have included into the mean equation. So here RT is the dependent variable, basically return. So mu is the constant, lambda is this lambda parameter, what we call that risk premium parameter, measuring the impact of volatility on the mean. This FHT is the function of the conditional variance. It could be that we can have square root of HT or simply HT we can include. And the variance equation, as we have in the GARCH 1.1, we have the same variance equation here. So only addition we are doing, that we are including a conditional variance into the mean equation. So why we do that? So basically what we know that risk and returns, this directly links the volatility to the mean equation. Why we have included that? A lot of investors, they are the risk averse. To attract that, what we have to do, we have to pay the higher premium in form of return. That means there is the relationship between the risk as well as the return. So higher the risk, there will be higher the return. However, in the GARCH model, we are not including that into the return. So here in the GARCH in mean model, by including the variance, we are linking the return with the risk. So now if the value of HT, that is the conditional variance in the mean equation, increases, then the return will also increase depending on the value of lambda. Therefore, we call it the risk premium measure. So and that is reflected by the lambda here. Another key feature is that it is the flexible, supports a different function of the conditional variance into the mean. We could have square root of ht, that is the standard deviation rather than variance, or we could have ht, that is the variance. Another feature, it brings all the volatility dynamics as we are able to capture through the GARCH-M model. However, there is certain limitation. First limitation, it becomes very computationally intensive to estimate a GARCH in mid model compared to the standard GARCH model. Second, again, it assumes a linear relationship between risk and returns, though it could be non-linear in the nature. Third, the interpretation of lambda depends on the functional form of this particular conditional variance term into the mean equation. Then there is another extension we have, what we call the T-GARCH or the threshold GARCH model. We may recall that one of the major restrictions of this ARCH and the GARCH model is that they assume there is the symmetric effect of the positive and negative change on the volatility. However, we know that in reality there is we have the different effect of the positive and negative change. So this GARCH models, so basically what we'll have, a big positive shock will have exactly the same effect on the volatility of the series as a big negative shock of the same magnitude. However, quite often it has been observed in equity market, for example, that negative shock, that is the bad news in the market, have a larger impact compared to on the volatility compared to the positive shocks or the good news of the same magnitude on the volatility. Then this T-GARCH, we add a particular term into the variance equation in multiplicative form to capture that asymmetric behavior into the response of volatility in response of bad news and good news. So the mathematical formulation of this particular model we can write like this, where this HT, that is the conditional variance. Now this part we have the GARCH-M model. Here we are adding another particular term which will basically capture the asymmetric behavior of the volatility towards to the good news and bad news. Now this dt takes the value of 1 when epsilon t is less than 0, that is when there is a negative value, otherwise it is 0. Now good news and bad news have the different impact. That phenomena is captured through this. When you have good news has an impact through the alpha 1 and the bad news has impact alpha 1 plus theta. Why? Because when it is less than 1, then only it is 1, otherwise it is 0. Then this whole term becomes 0 when we have positive change. However, this particular term becomes 1 when we have the negative change into the epsilon. So when we have negative change, this becomes 1, then we have this particular term. Otherwise, when it is positive, this particular term is 0, then this whole term becomes 0 and it becomes nothing but the standard GARCH-M model. So if theta is more than 0, we conclude that there is a symmetry. If theta is equal to 0, that means the news impact is symmetric. Then we have another extension of this GARCH, what is known as the exponential GARCH model, which was introduced by Nelson in 1991. It extends the traditional GARCH framework to account the leverage effect. So what we have leverage effect, the negative shocks often increases the volatility more than the positive shocks of the same magnitude. So to include that, what we have this particular formulation, where the mean equation is yt is equal to mu plus epsilon t. However, in the variance we have this term and this particular term. To have the to capture the leverage effect. So here alpha is the magnitude effect and gamma is the asymmetry effect or the leverage effect parameter here. And another thing what we are taking here that we are using the log of variance rather than the absolute variance here. So because of that we have the two benefit or two improvement compared to the standard GARCH model. One, it is able to capture the leverage effect through this structure here. On the other hand, when we are using the logarithmic transformation, then automatically inherently this GARCH model ensures that the variance is positive. There is no need of any additional non-negativity constant on the parameters. So these are the two improvements we have when we are using the GARCH extension of the GARCH model. However, there are the certain limitations we have. The first limitation we have, this logarithmic variance can be less intuitive than the variance into the standard GARCH model. So interpretation is very, in the limited sense we have the interpretation of here. Second, there is this computation becomes quite intensive, requires more sophisticated optimization technique for estimating the parameters, and it is slightly more computationally demanding than the standard GARCH model. Second, there is a further extension of GARCH. What we have the GJR-GARCH, which is basically is named on this three economists we have introduced this particular extension, that is Gloston, Jagannathan and Rankal in 1993. It is again an extension of the basic GARCH model. So in standard GARCH models assume a symmetric response to the positive and the negative shock. However, in the financial market, we have seen that both it has a different effect on the volatility. So to capture that again, the GJR model has given a different mathematical formulation of the basic GARCH model. So what is the formulation we have? We have this particular formulation. We have the mean equation. As usual, we have where this yt is mu plus epsilon t. Here yt is the dependent variable. It could be returned, so then we could write rt. And in the variance equation, we have added this particular term here. So what it suggests? It suggests that this sigma epsilon t minus 1 here, this one. So here what we are capturing, I into epsilon t minus is the indicator function equals 1 only when this epsilon t is minus 1 is less than 1. If this is not less than 1, then the value of I becomes 0 and this particular terms becomes 0 and we have a standard GARCH model. However, when it is less than 1, then we will have this particular term which is in addition of the normal effect wave. So that is, if there is a negative change or negative fluctuation, then we will have an additional term reflecting that the volatility will be more, that is asymmetric. The positive change has the different and negative change has the different effect on the volatility. That particular phenomena we will be able to capture using this the formulation of GJR-GARCH model. So what is the key features we have? It can capture the asymmetric phenomena of the volatility. Second, this indicator function is being used, which is quite simple to include, and the flexural dynamics, that is, it retains all the features of the simple GARCH or the basic GARCH model, and it provides a better fit for a financial time series that exhibits a asymmetry in the volatility. What are the drawbacks we have? As we have added more and more parameters here, obviously it increases the complexity. Interpretation challenge, how we should interpret the parameter lambda. Third issue, we have the estimation issue. It becomes quite a advanced technique we need to optimize the values. Assumption of specific asymmetry relies on the indicator function, so which assumes a particular form of asymmetry. However, asymmetry could be in another form. So today we have discussed an extension of the GARCH model, and we have also discussed the different extension of the GARCH to accommodate certain specific aspects of the volatility observed among the financial data. So in the next class, we will discuss about the stochastic volatility and its different extensions. Hope you are enjoying the class.